Okay, welcome to Unit 2 on filters, note set 4. And I've alluded to the idea that we can use all-pass filters to build other kinds of filters. And that's what we're going to do. And particularly for audio applications, we're interested in kind of getting a parametric um, implementation of these filters. We'll be somewhat successful at that, not completely, but it will allow us to have some nice forms for filters that would allow an easy adjustment by a user, so that we don't have to necessarily change all the parameters of the filter, all the coefficients of the filter. And we've got a few different places where this is covered that I'm loosely basing these notes on. So we've talked about all pass filters already. There's a picture here from Zolzer's edited book, DAFX. And basically the magnitude, we're showing the magnitude, the frequency response here is just perfectly flat. It doesn't have to be at 1, but is often just held constant at 1. So what good is that? Why is this useful? It doesn't seem like it would be useful. All frequencies just pass equally. Well, the interest is in the phase, as we'll see. And mostly for our use here, although there are some uses in audio and other areas where they're applied just to kind of change the phase of some other existing system. What we're going to look at them for is combining all pass filters together and using them to build other types of filters. So a low pass or a high pass, or low shelf or high shelf, or things like that. So that's the idea. So just like we did in some of our previous note sets, where we start with continuous time view and then go to discrete time view, namely by applying the bilinear transform, we're going to do the same idea here. So let's start with first order, continuous time, all pass filters. And my claim is that this is such a filter. Really, that's just one of two ways of doing it, and both of those ways are essentially the same. So that's the claim. We should take a look at whether we can verify if that does indeed give a all-pass filter. It's first order because there's just a single pole. Okay, so that's how we measure order of continuous time filters. So we convert the S into j omega, so we get a minus j omega up in the numerator and a positive j omega in the denominator. And if you're clever, you can start to see why the magnitude of this is equal to 1. But we'll go through the steps of that. But here's the pole zero plot. You can see that if we find where the pole of this is, it would be at minus omega c. And if we find where the 0 is of that, it would be over here at plus omega c. And here, as is probably clear, omega c is taken to be a real number. That would be consistent with our rational, real, causal, stable characterizations that we looked at a while back. And we note, and this observation will be extended, that the 0 is just the mirror image around this j omega axis. So wherever the pole is over here, this is just a mirror image on the other side of that j omega axis. And that will be a characteristic that is inherent to all pass filters, continuous time all pass filters. So like I said, we should verify this. And also, like I said, if you're clever and quick, you should be able to look at that and kind of do a little bit of steps in your mind and say, yeah, I see how that's happening. But so we have rectangular form over rectangular form. So there's our rule applied to numerator and denominator for finding the magnitude of something in rectangular form. And here's the thing, right? Minus omega plus omega, both squared, those become exactly the same thing. And so the numerator and the denominator magnitudes end up being the same, and we get that this is equal to 1 for all omega. So yes, indeed, we have shown that this is an all-pass filter. We can now find the angle of this, so we've got rectangular over rectangular, so we do the atan of minus of the imaginary part over the real part for the numerator, minus the angle in the denominator. So there's the negative sign coming from the fact that we subtract the angle in the denominator, and then it's imaginary part over the real part. Now, just a word of caution, if you're calculating this, the atan part will cause problems in general when the real part is negative. But for our case, this omega c is going to be a positive number, so that won't be a problem. But remember, MATLAB has a command atan2 that would be better used to compute these kinds of things. Okay, so now we can see a property of arctangent is that arctangent of a negative angle is the negative of the arctangent of the angle without the negative. So in that case, we can pull this negative out in front, and we have the same thing twice. So we have minus 2 atan of that thing. And we can check to see what is this omega c really representing. So if we plug in omega c, we get arctan of 1, and that turns out to be pi over 4, but then you have the times 2, and you get minus pi over 2. So that's equivalent to minus 90 degrees. And so we say for an all-pass filter, first order, the cutoff is where the phase hits minus 90 degrees. And so you might wonder, how do we specify the cutoff frequency of an all-pass filter since the magnitude stays flat? Well, that's how we do it. And here's a plot of that for the case of FC equals 1 kilohertz. So we would take the 1 kilohertz times 2 pi to get the omega c that would be used in here. And you can see I've plotted this on a log frequency axis and the phase in degrees. And we can see that at the specified cutoff frequency, we do indeed get minus 90 degrees. Okay, there is an alternate form. So the only thing that I've done is multiply the whole thing by a negative sign. So if you look back at what we had here for our transfer function for this, if I multiply the whole thing by a negative sign and pass that through just in the numerator, I get a plus there and a minus there. And so that's what we have here. And so multiplying a transfer function by minus 1, as far as frequency response, it doesn't change the magnitude at all. So we've already proved that this is all pass, and this negative out in front retains that all pass. But from a phase shift point of view, multiplying by negative 1 corresponds to a 180 degree phase shift. So we can go through and do the analysis as well. But what we would end up with is what we had before with a pi out in front. That's from the 180 degree phase shift. And so we can check again and see that when we evaluate this at omega c, we now get plus pi over 2 rather than minus pi over 2. And we get a plot that looks like this. So now this goes from 180 down to 0, whereas for the previous version, it went from 0 down to minus 180 degrees. So that's really the only difference between these. And we'll sometimes use one and sometimes use the other when we're using all-pass filters to build low-pass, high-pass shelves and so forth. All right, well, that's first order. Let's look at second order. And so what we're going to do is start with our standard form for the quadratic denominator polynomial. And recalling how Q and zeta are related to each other. We covered those in a previous note set, a couple note sets back. We remember that zeta less than 1 gives us complex roots, and we can use those two things together to establish that Q greater than a half gives complex roots. And that's the usual case of interest here, but not necessarily set in stone, but that's the scenario that we're mostly going to look at. So let's consider that we have complex poles. And remember, we talked about how as Q changes, these poles would move around this circle with a radius of omega c, and then they could get repeated at that position, and then they could move on the real axis. So we could do that. But like I said, we're mostly interested in the case where we have complex roots. And if we analyze this up on the top, we'll see that we get zeros over here. And yes, those zeros, all of the poles and zeros will all lie on a circle of radius omega c, and the zeros will be mirror images of the poles. So we saw that for the first order case, and now we're seeing it for the second order case. And because of that, we could rewrite our transfer function in the following way. Choose P so that this term gives us one of these. Doesn't have to be that one, could be the other one. And then P conjugate would make that term give us the other one, because these are complex conjugates. And then negating that, so S negative P. Now here's a little tricky. We say that they're mirror images, but really this makes it go over here. So these two are together, and those two would be together mathematically. But because we have conjugates and conjugates, we can just simply think visually and graphically that they're just mirror images across the JMEG axis. So that's not quite describing the mathematics, but it is describing that. So P is a complex number that defines one of the pole locations, and then you can get all the others locations from that. So, this idea of mirror image poles extends to higher order all-pass filters. So we can write out a general continuous time all-pass filter in the following way. We have a bunch of poles down here. They don't have to be like on a unit, or, on that circle. We can pepper them around however we want, but we have to make sure that any pole that we put into this product will have its complex conjugate in there as well. I decided to, rather than trying to make this more complicated notationally, I would just say off to the side, oh yeah, anytime you put in a piece of I that's complex, you have to also include a piece of I that would be the conjugate of that. And then the same thing up here, since they're just going to be the negatives of each other. So you can see that structure. And we can put a plus or minus out in front. That follows what we saw for the first order all-pass filter, where we could put a negative sign out in front and still get an all-pass filter. So I didn't go through all the steps, but if you actually multiply these things out, taking this into account, and multiply these things out, you'll find that what you get, and you can kind of see that whatever I define as A of S here will turn out to be A of minus S with a minus 1 to the nth power out in front. So that can actually be shown. And then we can show that if A of S is a polynomial that looks like this, A of minus S will have negative coefficients at all the places where there will be odd powers here. And again, that allows us to account for things like that out in front. So this is our general form. So the key thing to look for is you look at the denominator and then you look for alternating signs. That's a key sign that this is going to be an all-pass filter. So there's two ways that we can check. We can check with this mirroring idea, and this actually tells us that that we've got that mirroring action going on. But we can also look for the numerator's coefficients are the same as the denominator in magnitude, but they alternate in sign. So two easy ways to check and look and see if it's an all-pass filter. So that's all continuous time. Let's go into the discrete time world. So we saw that there was a relationship between the poles and the zeros. So the poles had to be in the left half side of the plane, and then the zeros are just mirror images on the right half side of the plane. We're going to see a similar relationship. Similar, not the same, but a similar related relationship for discrete time. So it's going to take us a little bit of work here to set up some notation to think about this. But here's the general form for discrete time all-pass filters. So we start by saying, let's create a polynomial, and we've just defined some coefficients there. And this is an nth order polynomial. And we're going to use a fancy name for that. We're going to say that make sure that we pick the coefficients such that that polynomial is so-called minimal phase. And all that really means is all of its roots are inside the unit circle. Okay? So there's a reason it's called that, but it's not important for what we're doing here. And now we're going to define a new polynomial, p tilde, using this machinery right here. Z is going to get replaced by Z inverse, so all of these will become positive powers, and then we multiply by a Z to the minus n, which will convert everything back into negative powers, but they'll be in the reverse order, right? So think about it. This one here gets multiplied by Z to the minus n, so that 1 will end up out in front of Z to the minus n. And then what happens here? This action makes this become Z, and then multiplied by Z to the minus n makes it become Z to the minus n minus 1. And so the P1 is going to be in front of that. So we see that if they go in this order, going from Z power of 0, Z to the minus 1, all the way down to Z minus n, if we keep the powers in the same order, the coefficients go in the reverse order for that polynomial. So that's just by definition right now. We haven't said anything about all pass filters, but now here it comes. If we note that because of this structure, the roots of this p tilde are the reciprocal of the roots of p of z. So now let's use these two to make a transfer function. So we're going to put our original p of z down in the denominator. It's minimal phase, so it will be stable. Then we're going to put the p tilde of z in the numerator. So it will have zeros that are the reciprocals of those. And then we can put a z to the minus k, where k is some integer that is non-negative. And that just imparts a pure delay on the filter. And sometimes we need that just to make the filter be causal and things like that. But the key thing is that we get some poles down here, and then the zeros are reciprocals of those. And so that is the new characteristic that replaces the idea of a mirror image. So we had for continuous time a mirror image across the j omega axis. Well, the unit circle for discrete time is playing the role of the j omega axis. And so we can't have mirror image across it. We have reciprocal across it. So that's the idea. So two ways to check. Look for the characteristic nature of the coefficients. Numerators are reversed order of denominators, or just look to see if the zeros are reciprocals of the poles. So let's get a discrete time first order all pass filter, and just like before, we're going to start with the continuous time all pass filter, largely because those are used in analog audio systems, and what we want to do is make sure we're getting something that is as much as possible mimicking that. So we start with the one that we started with at the very beginning, and we apply the bilinear transform. And if you work through that, you'll discover that it ends up looking like this, where the alpha is set based upon our desired cutoff frequency. And remember that cutoff frequency is where the phase goes to plus or minus 90, something like that, plus or minus 90 degrees. But look at that simple structure. Classic first order. And so now we can characterize the coefficients. I'm just telling you how I've defined the alpha here. We can end up getting a difference equation that looks like that. That's a nice form that we should try to remember. We can write down a block diagram for that, and that's a form that we should remember. So we do have one feedback path here and a feed forward path, as well as a direct feed through path. If we define these things as some intermediate variables, we can write some coupled difference equations to define this. So we can have a single difference equation, or we can have a coupled difference equation. So this almost, in fact, it does look like a state variable representation. So this would be the state dynamics, and this would be the output. Just another way of thinking about it. So they're just, again, restating what we got in some nice yellow boxes there and pointing out where the poles and zeros are. So if you find the poles of this, you'll find that you get a pole at minus alpha. If you find the zero of that, you'll find that you have a zero at minus 1 over alpha, reciprocally related. Remember, if we're finding poles and zeros by hand, it's best to convert that to z form. So I would multiply top and bottom by z in this case, and then find the poles of the numerator, or the roots of the numerator and the roots of the denominator. So if we choose alpha equal to minus a half, that's what our pole zero diagram is going to look like. And it's pretty clear there that we have a reciprocal zero, or that the zero is a reciprocal of the pole. And then if we plot this, you might wonder why I'm plotting this. Here's the K versus frequency. We don't really want to work directly with the K, but look at this. If we plot the resulting alpha versus the desired cutoff frequency, and I didn't quite go all the way to Fs over 2, because we would probably not want a cutoff frequency right up close to Fs over 2. But look, this isn't quite a straight line, but it's pretty close. And what that tells us is that we could build a little knob on our user input, and they could turn the knob to set a number between 0 and some maximum cutoff frequency. And then we could go through all this math, but we could just map this linearly, just draw a straight line from minus 1 up to 1. Minus 1 up to 1, and just have that be a mapping. And so that would be very easy to encode what was being put in on that dial that a user would use. It wouldn't be perfect, but for audio, we often don't really need things to be absolutely perfect, because a user is going to just kind of tweak that knob until it sounds the way they want it to sound. So that's the idea. And here I'm just showing that for this particular case, we'd be operating at that point. And so that's just pointing out, again, driving home this idea that there's this really nice, almost linear relationship that would make it very easy to make a user able to control the cutoff frequency of this. And then if we wanted to look at what the plot of this is going to look like, Here is this with the alpha replaced explicitly by the K. I guess I could have left that as the alpha there. And I've made a plot of the phase here for a cutoff frequency of 1 kilohertz, and I've plotted it over a very wide range of frequencies on a log frequency axis in hertz, and we're plotting the phase in degrees. And sure enough, since we used FC in here, 2 pi times 1000 will give us the omega sub c, and then we've used that in here. We should get this minus 90 degrees right at 1000 hertz. And notice, we saw for continuous time how this asymptotically approached minus 180 degrees, but for discrete time, we can only go up to Fs over 2, and that whole structure gets squished in. And so that's why we see that. When you see this kind of behavior, you know that a bilinear transform has been used. Okay, so now let's look at a second order discrete time all-pass filter. And we'll see that, we've already seen that the cutoff frequency is where the phase is minus 180 degrees, or something equivalent to that. It could be plus 180 degrees if we put a negative sign out in front. But that's the form that we're going to focus on. So I'm just showing you the generic coefficients over here. And I'm not going to go through all the details of that. But if we look at this parameterized by omega c, or equivalently fc and q, we can see that the omega c gives the k, and then we see that all of these coefficients end up having both k and q in them in a fairly complicated way. Now, in many applications, that's not a big deal. You just take your K, or you take your omega C, compute your Q, or your K rather, combine it with the Q to form these coefficients, and away you go. It doesn't quite work as nicely as we saw the parameterization between alpha, or the cutoff frequency in alpha for the first order, which was a nice nearly linear thing. But if we parameterize not by Q, but by FB, which is a bandwidth, we'll see in just a second how we define that. Now we get, it's still not completely decoupled because we do have a few coefficients here where D and C interact, but it's still much nicer and simpler for parameterizing this. And so I said F sub B was the bandwidth, and we then ask, well, we've already asked what's the cutoff frequency for an all-pass. Well, what's the bandwidth for an all-pass? So again, it's defined in terms of phase responses. So if the cutoff frequency is at minus 180 degrees, we go 90 degrees in both directions, and that'll be define F1 and F2. And then the bandwidth is just the difference between those two. So that's how we define the bandwidth. So just an alternate way of parameterizing these filters. Here's a picture. I can't remember what I picked here as far as FC. It looks like I picked 1K, 2K, 3K, 4K, 5K for that. And then what is this? This is 5K, that's 4K, 6K. I have it right up there. FC is equal to 5K, FB is equal to 2K, and our standard audio sampling rate. So we see where our poles and zeros are. We see the characteristic nature or impact of the warping of the bilinear transform. But because we did this with pre-warping, our FC ends up exactly where we want it to be. Okay, so nice, we've got those. So great, we've got all pass filters. What are we going to do with them? We're going to build other filters from them. So why would we do that? Well, it just provides a nice way of implementing them and sometimes we can gain some advantage because the coupling between cutoff frequency and bandwidth is a little less severe than what we might have otherwise. So if you go back to a previous note set, we listed the low pass and other ones. I'm just going to show you low pass here. In terms of the K and the Q, everything is very complicated and coupled. But we've already seen that these all-pass filters get a fairly nice, fairly decoupled form, and we can parameterize the all-pass pretty simply. And so that can save some complexity when we're trying to implement these things. So now, if we have an all-pass filter that is, somewhat decoupled like this, we may be able to then build other filters from it and end up getting a fairly simple parameterization. So let's look at how to build these. So it's all about the phase, remember, for all pass, and phase is something that can create constructive and destructive interference. So if we put in a sinusoid, and that sinusoid has a frequency where the phase shift going through the filter is 0 degrees, then the input and the output are going to be in phase. And if we were to add those together, they would constructively interfere. But if we choose a frequency where the phase is plus or minus 180 degrees, then for that sinusoid, the input and output sinusoids will be 180 degrees out of phase. That's just negatives of each other. And if you then add them together, they destructively interfere. So at frequencies in the region where the phase is 0, we will have constructive interference primarily. And in regions near plus or minus 180 degrees or any any odd multiple of 180 degrees, we will get things destructively interfering. And so constructive interference will allow us to make pass bands, and destructive interference will allow us to make stop bands. So let's just look at our first order all pass. And here we're plotting it F in hertz normalized by Fs. So in F alone, that's at the point Fs over 2. And we can see, as we saw before, that this goes from 0 to minus 180 degrees, as we would expect. So in this region down here, we're close to 0 degrees, so that's the constructive interference region. And here we're close to minus 180, so that's the destructive interference case. And then here's the other form of that. It looks like I have the same thing in both places. So this should just be a negative out in front of that. And so in that one, we have something that starts at minus 180 and goes to minus 360. So now we have destructive interference at low frequencies and constructive interference at high frequencies. This is when we add the input to the output, is when we're talking about getting this interference. So the point that makes the border between those two will define to be the minus 90 degrees. So we're going from 0 to minus 180. So minus 90 would be halfway between that. So whatever frequency we hit that at, that would be the cutoff between these regions. And same thing over here, we're doing it for the minus 270 point. So that's how we define those things. So now here we go. We're going to take our signal and put it through the all-pass filter, and then add or subtract the output to with the input. And so it's right here where that interference is happening. And so we can reason through from what we just saw that when we make it a plus here, we get a low pass, and when we make it a negative there, we get a high pass. So that's the idea. And so we're just taking that standard A of Z that we have here and either adding it or subtracting it to make this. So listen, this is how we write it out, but we wouldn't actually go ahead and do this manipulation ahead of time and then implement the result. Nope, we would literally implement it this way. We're just writing it out this way to say that's the final structure that we would get. And then here's some plots for that. These would look a little better if we were plotting them on a log frequency axis, but I just took the pictures from Zolzer's edited book, and this is what he had. But these do indeed look like low-pass filters and high-pass filters, just as we would expect. So that's nice. We can do a similar thing with second-order bandpass and bandstop filters. We can make those from second-order all-pass filters. So if we plug in our second-order coefficients here, as we've seen for the second-order all-pass filter, and we do this add and subtract thing, so that's what's happening here, we can look at the phase plots that we saw before and deduce that in the center of the band is when things are going to have constructive or destructive interference. And so we'll get either a band pass or a band stop kind of relationship. So that's nice. Again, this is how we would implement it. You don't really need to find that complete transfer function. That's not how we would do it. We would plug that in, implement that here, and then just add or subtract the input and the output. Let's make a first order low frequency shelf filter. Remember, we needed to do boost forms and cut forms. So let's start with the boost. We've already seen this before. I'm just changing the notation a little bit. I think I used G0 rather than H0 here. But everything else is the same. I'm starting with the non-normalized, or the normalized version of this, and just checking that I get the V0 gain that I expect at the low frequencies. Okay. Now we're going to denormalize that. So that just means taking S and replacing it by S over whatever our cutoff frequency is that we want. And so this whole thing now becomes this. And now what we're going to do is some algebra, because it's not clear how this is all working, because we want to get this into a form of an all pass. We started with a low pass there, remember. So we do a little bit of algebra here, and we're going to convert the low pass part here into something that uses an all pass. So that just comes from what we've already seen, how to build a low pass out of an all pass. So we've got that, but still it's a little clunky, so we should do a little bit of manipulation. Well, one thing we need to do is get over into the discrete time world. So we're just going to apply the bilinear transform and get the all-pass filter here. And I'm using the B here to denote that this is for the boost form. So here's our classic first-order all-pass filter, but how we compute the alpha is specific for the boost form. Okay, so we have that. And this is a very simple way to implement the boost version, but we're going to see how nice it is that we can just switch back and forth between boost and cut in a very simple way, and that's one of the beautiful parts of using all pass filters here. So let's look at the cut version of this, starting with the non-normalized form. I'm just going to jump right to that. So if we go back and look at what we had before, we'll see something that looks like this, although I've changed the notation just a little bit. And so that's what we've seen before for the cut version. And I'm doing it just a little bit differently than I did before so that we can use V0s less than 1 for the cut case. So now we do a little bit of algebra, and that converts us into this form. So again, we have a low pass filter here. We've converted it into using an all pass filter together with the one to make the low pass filter. And now we apply the bilinear transform and we get something that looks like this. So the form of this is exactly the same. It's just how we compute that is a little bit different for cut versus for boost. And now let's just compare them. We just see that the form is the same. It's just we compute the coefficients differently. So here's mathematically how we think about it, but really here's how we build it. We just have this A1 that we're implementing right here. And the coefficient that we use for alpha is computed this way for boost and this way for cut. And that's it. And so that's the beauty. Just plugging in one or the other will give us the boost or the cut. We didn't have to have two different forms to implement that flipping of the transfer function. Remember, we wondered, how are we going to end up flipping this transfer function? Well, this is effectively what we're doing here, just in a nice, convenient, clever way. Now let's take a look at the high frequency shelving filter. We'd go through exactly the same steps. I'm going to just do it quickly here. Start with the non-normalized boost form. Now we have a high pass filter here, which we're going to write in terms of an all pass filter. And then here's the form for the cut version. We start with the high pass filter converted into all pass form, and everything is nice as we would expect it to be before. And so now apply the bilinear transform and we get the same kind of idea. So this structure goes in here. What we use for alpha is computed one way or another way, depending on whether we're doing boost or cut. So that's the idea. And it works very, very nicely. Now, if we look at the two forms that we just got for the low frequency and high frequency shelf, we see that there's really just a very tiny difference between them. One had a plus here and one had a minus. So the plus gives us the low frequency shelf and the minus gives us the high frequency shelf. So now we have a very simple module that we can build. And depending on how we pick the coefficients and whether we put a plus or minus in there, we can get any form of these shelf filters that we want. Boost or cut, low shelf, high shelf, just simple building block that we can put in. And then the user input to choose which form can just come easily from a switch or whatever. Now, if it gets even better than that, if we look at this and we say, if we remove this upper leg, we end up getting something that looks like that, and we replace H0 by 1, now we get the low pass and high pass. So one little module would allow us to get all of these different filters. It's just very, very nice structure and makes it very simple to implement these things. All right, so those are shelves. Let's look at a peak filter, second order peak. And again, we had boost and cut forms. And so that's where we started with the boost and cut forms. And again, I've just changed the notation just a little bit. Mainly down here, I bring the V0 down in the denominator so that we can put a V0 less than 1 in there. And we could go through all the steps that we went through before, but I'm just going to skip over those, and this is what we would get. And we get a structure that looks a lot like that, or looks exactly like that. You can see that structure looks exactly like what we just saw for some of the others, with just slight little differences. So you build a little module and you can just plug it in and switch it into whatever form you want. And if you compare it to the form that we had for the bandpass filter and the band stop, you can see that if we get rid of that top there, we can get a second order bandpass filter very easily out of this. And so that's the beauty of using all pass filters. We don't really want them just for themselves. We want them as building blocks to make building blocks for other audio filters that are very generic and very configurable. And that just makes things work very, very nicely. In the next set of notes, I hope you'll show up there. In the next set of notes, half of it will be some further explorations of these structures with all-pass filters, and that's a structure known as the regalia filter, which is in a lot of the literature for audio signal processing. And then the second half will look at a really cool state variable-based filter that is widely used in lots of different audio applications. So I hope we'll see you there.